The biggest threat to drinking water safety is microbial contamination from fecal matter. Poorly constructed or protected water sources can become contaminated, or inadequate sanitation and hygiene can introduce contamination after water is collected. And because pathogens are so small, contaminated water might smell, taste, and look perfectly clean. So the only way to really confirm if water is contaminated is to do a test. And traditionally, this is involved using laboratories with specialized equipment and trained personnel. Now, laboratory testing is great, but it poses some drawbacks. First of all, distance. Laboratories might not be located near to the site where testing is being done. And since microbial samples should be tested within 6 or a maximum of 24 hours after collection, this has posed a real challenge. Laboratory testing can also be expensive, and it can be difficult to get the results from the laboratory back to the local authorities. However, technical advances have made field testing more practical, easy, and cheap. So some of these new options include most probable number methods, where a number of small compartments are tested and a statistical test tells you the most probable number of bacteria contaminants. Also, membrane filtration is increasingly done in the field. Also, new enzyme growth media react specifically with certain bacteria, like E. coli, the preferred indicator for fecal contamination, which makes results more robust. And then finally, there's a new generation of low-cost incubators that can be done without electricity, or at least away from a well-equipped laboratory. So taking advantage of all these advances, WHO and UNICEF have developed a water quality testing module which can be applied in national surveys. And this has been done and piloted in a number of multiple indicator cluster surveys, or MIX surveys. The package consists of 3 elements. One, a membrane filtration system made by Millipore, the microfill system. 2, growth media, Nisui compact dry EC plates. And 3, portable incubation, and this is body belt incubation. These materials are used by the mixed field teams after they go through a basic training. During the survey, the teams will ask the respondents for a glass of water that they would give a child to drink, and then they test that water. In some cases, they also visit the source where the water was collected and test that water directly at the source. And the way they do the test is they use a membrane filtration system to pass the water through a special piece of paper which has small holes in it. And the holes are large enough to let water pass through, but small enough to trap all of the bacteria on the paper surface. That filter paper is then placed on some growth media with all the food and water that the bacteria need to grow, and left for 24 hours so that bacteria can grow and form colonies of billions of cells which become visible to the naked eye. Once the colonies have grown, they can be counted and the results can be recorded and shared with the communities. In these field tests, the mixed teams actually test 2 samples, a 100 milliliter test for low contamination and a 1 milliliter test for high contamination. And this is because if there's a large number of bacteria in the water, then they can form so many colonies that it's difficult to read. So for highly contaminated samples, a 1 milliliter sample is the best option. Now let's look at what the testing equipment looks like. The first part of the kit is a filter instrument, or manifold, and this one is produced by Millipore as part of their microfill line of products. The filter instrument is used with a filter paper and a plastic funnel, also made by Millipore. These are sterile and disposable. You need to use 1 per sample tested. And we also use a simple plastic syringe to create a vacuum and filter the sample. The test requires a number of small accessories: forceps to handle the filter paper, an alcohol wipe to sterilize the instrument and forceps, a small plastic syringe to rehydrate the growth plates, and a permanent pen for marking the growth plates. Finally, you have the growth media. There are many options available, but we use an enzyme growth media produced by Nisui called compact dry EC plates. These come pre-packaged and foil wrapped in sets of 4, and the nice thing about this packaging is that the plates can be stored at room temperature for up to 18 months. So let's see how this test works. The first step is to get all of our materials together and label the two compact dry plates with that pen. This is a sample of lake water. Okay. I've got a glass of water I collected earlier from Lake Geneva. Let's see what's in it. Next, we have to make sure that our hands and our equipment are all clean, and we will use a simple alcohol wipe to do this, to sterilize the forceps and the manifold, and some alcohol sanitizer for the hands. Could also use soap and water if that's more convenient. So with the alcohol wipe, first we sterilize the forceps. And then the part of the manifold that will touch the filter paper. And here it's good to use the forceps to stabilize the manifold. Okay, then we're going to put down the forceps on a clean surface to keep them sterile. And the next step we're going to do is take the sterile filter paper. Now, the Millipore filter paper comes with a protective blue sheet, which is not the filter paper. You don't want to use that. So what I like to do is first take out and remove the blue paper, and then take the white paper with the gridded side up and place it right on the manifold. Still need to keep the forceps clean. But now we're ready to put the plastic funnel on. And the plastic funnels are also sterile. They're kept in these plastic sheets. So you just reach in and take one out and put it directly on top of the filter paper. There we go. Now we pour the water into the plastic funnel up to the line on the funnel that's marked at 100 milliliters. And a little bit more or less of the water doesn't matter. We just want to know the general level of contamination. Now we need to rehydrate these compact dry plates. We'll take the lid off of them, of the two of them, and open this 1 milliliter sterile syringe. Draw up 1 milliliter of water from the funnel and place it on each of the compact dry plates. Now the plates, they have food for the bacteria, but the bacteria can't access the food unless they're rehydrated, so it's important to add some water. That's done. Now for one of these, the 1 milliliter test is complete, and we can put the lid on it. For the other one, we'll filter the water through the paper and put the paper on it. And to do that, we'll use this 100 milliliter syringe. So we just attach the syringe to the side of the instrument and pull it gently to suck water through the membrane. Remember, the holes on the membrane are small enough to trap all of the bacteria on the paper. So whatever bacteria were present in this sample of lake water are going to be on that filter paper when we're done filtering it. Just takes a few minutes. Okay. Sometimes you need to remove the syringe and do 2 batches, like we've just done here. Okay, there we go. We've got all the water out. So we remove the plastic funnel. We're done with this now. Use the forceps to remove that paper and put it directly on the growth media. Now we put the lid back on it, and we're done. We just have to clean up now, make sure that we take all the waste materials and throw them away. In fact, it's a good idea to have a rubbish bin when doing the test in the field, because there's not always a good, safe place to dispose of wastes. So now we have bacteria on the plates, they have food, they have water. All they need to grow is some warmth and a little bit of time. Now, E. coli will be happiest when the temperature is around 35 to 37 degrees, though they will grow at temperatures down to 20 degrees, though it takes a bit longer. If the temperature gets above 40 degrees, they don't grow well on this particular media. In a laboratory, you have electrical incubators that can regulate the temperature very nicely at the desired temperature. But for this field testing, we don't have those. But there are some newly developed alternatives that we can use. The first is to use an electrical incubator, but a small portable one like this one that can run on electricity if you have it, but could also run on batteries or plug into the cigarette adapter in an automobile. So there are different versions of this. It's a nice option. A second option that's under development in the research stage is called a phase change incubator. And this is an example that was developed at the University of Bristol. And what it does is, it's like a thermos. And you fill this thermos up with boiling water and let the water sit for about half an hour. Throw out the water. And then the thermos retains the heat from the boiling water. And if you place the plates inside and close it, the incubator will keep the temperature at about 35 degrees for over 24 hours. So this is a very nice technique that doesn't require any electricity at all. But there's another source of heat available in these surveys, which we've used in the mixed pilots, and that's the body heat of the survey team. Human bodies are about 37 degrees, which is a perfect temperature for incubating. So the NGO called ENFO in Nepal has developed a body belt incubator to take advantage of that body heat. And this is just a fabric belt with some pockets sewn into it. You can insert the plates into the pockets. And then wrap it around the waist. And voila, you become a human incubator. And this has proved very successful in field trials so far. There's a fourth option available, depending on the climate, which is just to incubate the plates at ambient temperature, normal room temperature. And if you're in a country where the temperature is above, say, 20, 25, ideally 30 degrees, that can also be a good option. Once the samples have been incubated for 24 to 48 hours, we can count the colonies. Now, E. coli bacteria will form blue colonies on the compact dry plates, and other coliforms, like total coliforms or thermotolerant coliforms, will produce red or violet colonies. Here are some examples. Now, other bacteria can also grow on the plates, but they will form colonies that are white or pale yellow or some other color, but those are not coliforms or E. coli, so we're not concerned with those ones. Once the colonies have formed, we can simply count the number of blue and the number of red or violet colonies and record the results. If the plates have very high levels of bacteria on them, it's difficult to see individual colonies, and you can have plates that are overloaded, which look completely pink or completely blue. Once the results are recorded, they should be shared with the local authorities or communities, and then the plates should be disposed of safely, which means that they should be disinfected using either chlorine or heat and then disposed of. Well, let's look at some of those results. The first sample I showed you was lake water from Lake Geneva. And you can see that this water actually has quite a lot of bacteria in it, a lot of those red and violet colonies, more than 100. And when it's above 100, we don't even bother counting anymore. But it's only got about one of those blue colonies, which means E. coli. Now, a second sample that I tested was taken from a toilet, and in this water, we see that there are lots and lots of those blue colonies, E. coli, more than 100 of them in the 100 ml sample, but none at all of those other coliforms. And that makes sense because the toilet water is full of fecal bacteria. Once the data are recorded, they can be analyzed and presented. But it's important to know that the data are of good quality, so we have some consistency and quality control checks that should be applied. A consistency check is comparing the results from the 100 ml test against the 1 ml test. Now, of course, the 100 ml test should have about 100 times as many bacteria as the 1 ml test. So if that ratio is very different, there might be a problem. It's also good practice to have some blank samples to make sure that people are getting zero counts when the water is known to be free from contamination. And it's quite valuable to have expert teams visit the field teams as they're doing the field work to make sure that they're doing the test correctly. Once the quality of the data are assured, though, then we can classify the results into risk classes. And normally we look at less than 1 E. coli as meeting regulatory guidelines, 1 to 10, 11 to 100, and 100 or more colonies representing increasingly dangerous or high-risk samples. The mix team has developed standard tables and scripts for the statistical software that analyzes the data to make it easier for countries to standardize their analysis. And then the results can be presented either in a standard summary report with the rest of the information collected in the mix survey, or in a special focused thematic report that can go into more detail about the water quality testing results. So, we've seen a demonstration of a testing package for E. coli that's easy to implement in the field without need for electricity, laboratory facilities, or highly trained technicians. By relying on pre-packaged materials, the system reduces the opportunities for contamination to be introduced, though it's still important to include quality control and assurance measures like regular testing of blanks. The system is not very expensive, and especially when it can be linked to an ongoing and already financed field program, the data collection can be very cost-effective. This system has been applied in mix and other national household surveys, but could also be useful for general programmatic use. As an example, in Bangladesh, after this system was used in a mixed survey, the UNICEF office used the materials to do water quality testing of water supplies that had been installed in their program areas. Of course, we need to remember that a single measure of E. coli is not a robust measure of water safety. For that, you would want water safety plans or at least sanitary inspections. But for getting a rapid assessment of drinking water quality, or for monitoring an intervention like a household water treatment intervention, even a limited amount of microbial testing can be very helpful and can help identify problems and direct resources towards improvements.